All right, so in example 5, we're going to take a look at some polar area that involves two graphs at the same time. So the first one we're looking at is the graph of r equals 3 sine theta, and the second one is r equals 2 minus sine theta. And we're trying to find the area that is inside the first one and outside of the second one. So this is where being able to sketch them is especially crucial, so that you have an idea of what it is you're even looking for. So first let's take a look at the r equals 3 sine theta. So this is the kind that's just a circle. It's got y-axis symmetry. I'm going to be lazy and abbreviate. And then these tend to have a period. They're one of the shorter ones of 0 to pi. So we know that sine starts at 0. The 3 is going to be the diameter. So it's going to go up to 3 and then back to 0. And this is occurring from 0 to pi over 2 and then to pi. And we can go ahead and label down here just for good measure. Now the second function is r equals 2 minus sine theta. So in this particular one, our shift is greater than our amplitude, so we're not actually going to reach the pole, right? So this is the limacon without a loop. So let's think about how we would start graphing this. And for this one, I might use a table just because sometimes that helps me. So if I'm thinking of r theta, that's going to be, normally we start at 0. So sine of 0 is simply 0. So that's just going to have a radius of 2. So that's going to put me, I don't know, maybe around here. And then let's plug in pi over 2. That's going to be 1. So 2 minus 1 is 1. So it's kind of making that guy. Then we normally plug in pi. Sine of pi is also 0, so we're going to go back out to 2. And then 3 pi over 2 is going to be negative 1. So since we're doing 2 minus this value, that's really going to be like 2 plus 1, which will take us all the way down to 3. Right? And then of course when we get to 2 pi, that's going to be just like it was for 0, so we're going to get a 2 again. And that completes the cycle. So this one has a period. This one is a limacon without loop. It's from 0 to 2 pi. It also has y-axis symmetry. Okay. And now let's revisit the actual question. It says find the area inside the circle. So inside the circle and outside of the limacon. Okay, so we're kind of looking for this weird area here that's inside the orange circle but is outside of the limacon. I guess it kind of would have made more sense to do this. All right, so the area we're actually looking for is this right here. All right, so I'm going to use another color just to make that as clear as I can. So, what I want you to do is think back to what we did when we found area between two curves, right? Or not even area, but volume. We would be rotating volumes with different radius lengths, like with our discs, where we would have a long radius and a short radius. That's kind of the idea that we're going to be going with here. So let's think about this. Just like our other graphs, this is a very symmetric graph. So it would be great if I could just get this half here and then multiply it by 2. And so for now, it seems like what I'm most concerned about to find that area is where the two graphs are intersecting, which I don't know this actual angle at the moment, right? We're going to call this theta just alpha. And then through the halfway point, which we actually do know the value of, that's just pi over 2. So the first thing I'm going to try to do is figure out what is this intersection point. Of course, we're going to kind of use our properties of equations to figure this out. So I want to know their point of intersection, which I'll abbreviate. So I'm going to take, 3 sine theta, and I'm going to set it equal to 2 minus sine theta, and see if I can figure out where this point of intersection is first occurring. Now with polar functions, you have to be careful because your eyes can be deceiving here. We're used to working with rectangular graphs where if they intersect, it's definitely visually where we see the intersection occurring. But with polar graphs, you have to take into account the speed component of how fast this is actually tracing the curve versus how fast this graph is tracing the curve, right? It's like if you see tire tracks in the snow that cross each other. Just because they intersect doesn't mean that two cars actually collided, right? There's no guarantee that they crossed at the same time. So that's what makes these a little more complicated, again, than rectangular. So we have to look at it from an algebraic perspective to kind of double check that they're actually hitting this intersection point and not simply that this graph got there and then this one crossed after. All right, so to solve, we're going to add sine over, which would give us one more than what we already have. And then we're going to get sine of theta equals 1/2. And this occurs at two places, pi over 6 and 5 pi over 6. Again, we're concerned with this first intersection point. Obviously, we could use the second one and find that half and times by 2. Just with the way I've drawn it, I'm going to stick with pi over 6. Okay, so that's going to be the alpha of my integral, and then pi over 2 will be the beta, but now we need to set up the rest of it. So the next, part of the puzzle is how do I represent this green area, right? It's the difference in the radius expressions of the other two graphs. So this is where it should feel familiar to what we've done previously with area and volume. We're going to take the one that is further out and subtract the one that is closer to the pole because we want this particular area here. So let's go ahead and start setting all this really fun situation up. So we're using symmetry, so we're going to be doing 2 times whatever I'm about to write. I'm going to do 1/2. I know I'm going from pi over 6 to pi over 2. Okay, of the further out graph, which in this case is the 3 sine theta squared d theta, and I'm subtracting from it that smaller area that we don't actually want, which is what's enclosed by the second graph of, let's make sure I don't run out of space. What is that? 2 minus sine theta. Now, this graph is actually kind of nice for a variety of reasons. First of all, we know that the 2 is going to cancel out with these fractions out front. And the second nice thing about it is that our bounds actually match here. So this means we can type this in our calculator in a much more simplistic way than how we have it written currently. And the way that we're going to do that is I would definitely type this into R1 and I would type this into R2. And so when you're actually going to evaluate it, because they both go from pi over 6 to pi over 2, we would simply find the difference of R1 squared minus R2 squared d theta. And that would be really all you'd have to type in at that point. And it would give you an estimate of approximately 5.196. And that's that.